So let's talk first just a little bit about microwaves themselves. Microwave, the word, just refers to a very specific band of the electromagnetic spectrum, and it's commonly accepted that microwaves, micro, lowercase mu, those are circuits that operate in the frequency range from 1 to 40 gigahertz. So if not gigahertz, gigahertz. So we're talking, gigahertz to 40 gigahertz. I've listed some common applications here in this table of microwaves. This is going to include at the low end in the 1 to 2 gigahertz range the global positioning satellites and your personal communications devices, cell phones, stuff like that. From 2 to 4 gigahertz, we've got microwave ovens. We've got still other personal communication technologies, just certain types of cell phone networks. From 4 to 8 gigahertz, we're talking about satellite communication. So this is satellite to ground and satellite to satellite based communication. 8 to 12.5 gigahertz, these are the ground radars for aircraft navigation. So these are the radars that are in air traffic controllers that are giving information to airplanes. So those radar dishes operate in this range. And then we've got, in much higher frequencies, we've got point-to-point radio and other radar applications. I've listed the IEEE standard letter designation. You may have heard these before. We're talking about the L band, the S band. These refer to bands of the electromagnetic spectrum, and it's just another way to refer to what slice of spectrum or what slice of frequency that you are actually using. And you don't need to know these for the course. I just am giving you a little tidbit of information about some of the ways that radio geeks would refer to some of the band that we're talking about here. I guess I kind of like microwave ovens, by the way, because at 2.45 gigahertz, they're power microwave devices, right? They're putting power into your food. These are producing like 1.5 kilowatts of power sometimes to cook your potato or whatever, your macaroni and cheese, and where most of these are doing milliwatts of power sometimes. And so this one's kind of neat. In fact, it's a microwave circuit that involves high levels of power. Little technical glitch there, sorry. The vast majority of modern microwave engineering is really going to be in the signals and communications field. So these are, largely communication devices, Wi-Fi networks, Bluetooth networks, satellite networks, cell phone networks, things like that. For example, modern clock speeds of microprocessors, it's usually around 4 gigahertz. The GSM cell phones operate, 1.85 to 1.9 megahertz uplink and 1.99 to like 1.989, megahertz downlink. Wireless LAN uses spectrum in the 2.4 gigahertz, 5 gigahertz, 45 gigahertz band. And really, no matter the technology implemented, communication systems will typically use a transceiver architecture that is similar to what I'm showing here, and hopefully you've already studied this in your communications courses. So this is a radio frequency front end. We've got an antenna, and the antenna has a filter on it. It's called a duplex filter because the antenna is being used for both transmission and reception. In the case of reception, the received electromagnetic wave gets converted to a voltage and current, and therefore power goes through a low noise amplifier. The low noise amplifier, which amplifies the incoming signal, is then sent into usually a surface acoustic wave style band pass filter. We down convert the high frequency data by mixing it with a lower frequency signal generated by a local oscillator inside of a mixer. At that lower frequency, the intermediate frequency, we then amplify that signal. We do some analog to digital conversion. We can send that to the microprocessor, which creates the data that your cell phone sees. If the cell phone is the source of the data and like a text message or something, it takes that digital data, it does analog conversion on it. We then have an up converter where we take that small signal analog. We then mix it with that local oscillator. We run it through a bandpass filter again. We pre-amplify it. We then amplify it again. We then send it through the duplex filter and out onto the antenna. So that's kind of the RF front-end topology. And the reason that this has become so dominant in modern microwave engineering is that at high microwave frequencies, we can get away with smaller devices. And that allows us to use conveniently sized antenna that can fit in, portable devices. Many years ago, antenna were very large, and by going to higher frequency, we can now create antenna that fit inside laptops, that fit inside of cell phones, and such things. In addition, high frequency just allows us to transmit more information. The bandwidth of a microwave frequency is about 30 times that of your standard RF frequency. So at higher frequencies, we can just transmit more data. And another advantage of microwave is that it's not easily interfered with. It has high directivity. We'll learn what that means, but it's basically that you can point microwave signals in a certain direction and they go in that direction. They don't spread out. So you can have an antenna and you can point the antenna. In electromagnetic language, you can point the antenna in the direction that you want it to send information, and it will do so, and it's not super easy to interfere with. But really, they're all advantages. I think the major advantages has been size. If we think about the fact that the lambda, or the wavelength of a frequency traveling in an antenna, is equal to the propagation velocity divided by frequency. Well, let's look at that in free space, because that gives us our worst case scenario. If we were to look at this in free space for microwave frequencies, we take 3 times 10 to the 8th, the speed of light, we divide that by the low end of the microwave frequency, 1 gigahertz, and we get a lambda is equal to 0.3 of a meter. If we were to do that at kind of the higher end of the microwave frequency band, we got 3 times 10 to the 8th, we divide that by 40 gigahertz, and that gives us 7.5 millimeters. You'll recall that the cutoff for when we have to apply electromagnetic analysis is lambda over 10 or lambda over 20, depending on which rule of thumb that you like to apply. So divide that by 20, and you get 15 millimeters. Trace length is the cutoff for the low end, and at the high end frequencies, the 40 gigahertz frequencies, the cutoff is 0.375 millimeters. And this is for in free space. These cutoff lengths for the transmission lines where we have to switch between lumped and EM analysis techniques would be even smaller when we consider that this is traveling in a conductor. And we'll talk about how the conductor and the material in a microstrip circuit actually affects that. So basically what I'm saying is the short wavelengths involved in microwave circuits as compared to the circuit length means that, like the T-lines we've been analyzing previously, we can't use electronic circuit theory to analyze microwave circuits, and instead we have to go to T-line analysis, and as we'll find out in the next lecture, we actually have to use a new technique called scattering parameters, or S parameters, and we'll apply those techniques today and hopefully in the next lecture. Circuit designs, as I'm showing here in this figure for microwave range, they're usually called MMICs, MMIC, which stands for Microwave Monolithic or Monolithic Microwave Integrated Circuit. And this here is, I'm showing a 2 to 18 gigahertz MMIC up converter. Typically, this involves 2 areas. We've got the active devices on one side that operate at microwave frequencies. These are your FETs, your amplifiers, etc. And then you've got the circuit board that's used to connect these devices. So the MMIC basically consists of 2 parts: the circuit board topology, which are these traces you're seeing, and then the active devices themselves, the filters, the FETs, and things like that. In this class, in electromagnetics, we're concerned with the interconnect layer on these MMICs. So we want to know about the strips of metal that connect these little active devices together. In subsequent classes to this, we're going to look at the techniques for the design, testing, and understanding of the microwave components themselves using something we're a little familiar with, these S parameters. And so that's kind of big picture what we're going to be doing with microwave circuits over the next couple lectures.